Welcome. This is the first of several videos that will go along with 9.1 from the IB Brown book talking about oxidation and reduction. So in this first video, I just want to introduce you to the terms oxidation and reduction and something known as oxidation states. So oxygen surrounds us, making up 20% of our atmosphere, and oxygen is really reactive. Remember, it's got a high electronegativity, so it's involved in a lot of reactions because it's reactive and it's constantly surrounding us. So oxidation is an old term that was used to describe the numerous reactions involving oxidation, such as burning, respiration, where we get energy, rusting, corrosion, all those reactions with metals, with us, etc. But what we now know is that oxidation is always accompanied by another reaction called reduction, which used to be thought as the loss of hydrogen. And it got the name reduction because it was often used to get minerals, to get a specific metal like copper out of the mineral, say copper sulfate. So we saw a reduction in size of that ore to when they got just the pure metal out. So the terms oxidation and reduction are actually very kind of old-fashioned terms, but we still use them, and they involve many more reactions than just those with oxygen or hydrogen involved. So we now know oxidation and reduction make up a process where electrons are transferred from one reactant to another. Remember back when we talked about ionic compounds, metals tend to lose electrons, nonmetals tend to gain them, and it's all about their size and electronegativity. And scientists now believe that many aspects of aging are due to repeated oxidation reactions in our cells that cause damage to the membranes and eventually the DNA, which would help explain why degenerative diseases like cancer occur more often as you increase in age. If you live long enough, you will get cancer or some of these other degenerative diseases. So the benefits of antioxidants, which are just what they sound like, they're antioxidants, so they prevent oxidation. These things found in fruits, vegetables, red wine, cocoa, and tea. The benefits are definitely known, but we don't completely understand them yet. So what is oxidation and what is reduction? Oxidation is the loss of electrons, while reduction is the gain of electrons. So we use the acronym OIL-RIG. Oxidation is loss, reduction is gain. In other words, it's the transfer of electrons. One's losing, one's gaining, has to be an equal number of electrons involved. So think ionic bonds, but remember, it could also happen with a covalent compound if there's an unequal sharing of electrons, which there often are with covalent bonds. So the transferring of electrons results in the flow of electrons, which is what electricity is. Thus, redox reactions can be used to generate electricity, like in batteries. In fact, they're referred to as voltaic cells, which we'll look at in 9.2. You can also have the reverse reaction. You can use electricity to force a redox equation to happen, which we call electrolysis. And that's important in getting metals out of the ores they're in. It's also important to get chlorine and hydrogen out of the compounds they're in. Plus, we use electrochemistry for plating metals on all kinds of things, from jewelry to statues to whatever. And it literally powers our tech-heavy world. So redox reactions represent both the oxidation and the reduction. It's one equation with both processes involved in it and represented in it. So a redox reaction is defined as a chemical reaction where there is a change in electron density, or in other words, the sharing of electrons. Electron density is how often, how tightly you're holding electrons to your nucleus. So the change in electron density is shown using this idea of oxidation states, or what sometimes people refer to as oxidation numbers. And you remember these. We said family 1 tends to lose 1 electron, so we give it an oxidation state of +1. Family 6 with oxygen in it tends to gain 2, so we give it an oxidation state of -2. So the term electron density is preferred instead of electron transfer because the transfer can be complete like in an ionic bond, but it can also be partial like in polar covalent bonds. So let's look at an example of a redox equation. So my example here, 3 magnesium plus 1 nitrogen molecule yields 1 magnesium nitride molecule. That's the full redox equation. But we could break this apart and look at just the oxidation part or the reduction part. The oxidation part would be the 3 magnesium breaking apart into or oxidizing to form magnesium ion. And I know it's oxidized because to go from 0 to +2 means that the magnesium has lost 2 electrons, or 3 magnesium have lost 6 electrons total. So I can see that this is oxidized because electrons have been lost. And remember, instead of showing minus, we just show what the reactant results in, or what the product is at the end. And then the reduction, I can see that these 6 electrons were gained by the 2 nitrogen in forming the nitrogen ion with the -3 charge. So you notice there were 6 electrons lost, 6 electrons gained, so our electron transfer is equal. And again, I can look at just the oxidation or the reduction part of this in what we call half equations. A little more on the oxidation state, and in the second video we'll look at some examples of how you determine it. But how do we know what the oxidation state is, especially with covalent substances? Because electron transfer is fairly easy to follow when it's an ionic compound. But let's look at the example of hydrogen and oxygen gas combining to form water. This equation is H2 plus O2 forms H2O. So to balance it, I need a 2 here and a 2 here. And as pure gases, both oxygen and hydrogen are diatomic, and they form pure covalent bonds. So the hydrogen shares that pair of electrons equally, and the oxygen in its double bond, it's shared equally. So each of these would be given an oxidation state of 0. Okay, there isn't any, neither hydrogen has more control over the electrons than the other. And then each atom, when it combines to form H2O, now things shift because oxygen is more electronegative. It's going to exert a greater pull. Remember, when we have an oxygen atom, it's very polar because there's a very negative end to the oxygen end, a very positive end to the hydrogen end. What that is showing is that change in electron density. Oxygen now is said to have an oxidation state of -2. It has essentially gained 2 electrons by pulling this shared pair much closer to it. And each hydrogen is said to have an oxidation state of +1 because it's lost control of its 1 electron. Now these electrons aren't actually transferred. This is a covalent bond, but we use these oxidation states of +1 and -2 to show the change in control over the electrons during this bond. So oxidation states are really made-up values to follow the oxidation and reduction, especially in covalent compounds where they're not completely transferred. It's a value assigned to each atom in a compound to show the element's electron control or possession compared to when it's a pure element, and then its oxidation state is always going to be 0. It hasn't gained or lost control, it's equal. It can be also thought of as the apparent charge the atom picks up when bonding. The positive charge indicates a loss of control, because remember, electrons are negative, so if you lose control, you'll be more positive. Negative charge indicates greater control. And the charge is always written first, followed by the number of electrons involved. So to sum up, here's what I've talked about in this video. Oxidation state is a value assigned to each atom in a compound that indicates the electron control compared to when it's an unbonded atom or element, which then we'd give it a 0. Technically, oxidation states are written with the charge and then the value, whereas ions are written with the value then the charge. So you see Fe plus 2 is its oxidation state. Well, Fe2 plus is telling you it's an oxidation, it's an iron ion. And there's 2 parts to an oxidation state. The sign letting you know if it's gained or lost control. Positive means losing, negative means gaining. And then there's the value referring to the number of electrons which it's gained or lost control over. And finally, remember, oxidation and reduction can be summed up with the acronym OIL-REG. Oxidation is loss, reduction is gain. You can't have one without the other.